Alright, so we'll finish up the practice test now. So number 20 and following those, first of all, 20 doesn't really have a lot of math involved. You just have to know how to use a calculator to do this. So the natural log of 68, show you how to do that. So, whoops, here we go. Natural log button is right there, 68. That means e to the what power equals 68, and it's e to that. Let's double check. Second e raised to the second answer does equal 68, so the answer should be 4.22. To nearest thousandth, I guess they didn't round that correctly. It should be 4.220. I guess it was right. Alright, so 21, it says solve each equation. So we want to take the log of both sides because that's the only way to get this. We don't want to divide by 10 because we see what's being done to x and do the opposite. X is not being multiplied by 10, so we don't divide by it. X is being raised to an exponent, and the opposite of raising to an exponent is taking the log of both sides. Okay, so even though it doesn't say that's log base 10, there's two ways you could do this. You could take the x and swing it in front right there, because we talked about that before. Or you could notice that the log base 10 of 10, that just equals 1. 10 to the what power equals 10, 10 to the 1. So that really just cancels out. And then we still have log of 42. So x equals the log of 42, the log base 10 of 42. When you plug that in a calculator, you get that number right there. And it says round to the nearest 10,000. 10,000 means 4 decimals. So you can easily check that 10 to that number should be equal to 42, and it does. Okay, these ones are a little bit harder because we have more stuff to get rid of first. So we cannot take the log of this until we first get rid of the minus 8, which we'll do by adding it. And then secondly, we have to get rid of the negative 80 plus 8 is negative 72. We then have to get rid of this negative 5, which is being multiplied. Okay, if you take the log before that point, the problem is not going to, it will be wrong. Negative 2m minus 3, and then negative divided by negative is positive. So 72 divided by 5 is 14.4, or you could just keep it as 72 over 5, it doesn't matter. Okay, now what we need to do is take the log of both sides. It doesn't matter what log you take, but usually we take log base 10 unless we're dealing with e. So the rule is you can now, once you've taken the log, you can't do this before taking the log. Once you've taken the log, you can now put this in front. And the mistake here is to write it like this. This is wrong because you're only multiplying 3 by that. You want to multiply the entire thing. So I need a parentheses there. And then this is equal to the log base 10, even though we didn't write base 10. That's what log means if there's no number. Okay, then we are going to clear out this log 17 by dividing both sides by log 17. And then, whoops, so we're going to need a little bit more space here. We'll have negative 2m minus 3 equals whatever this is. I'm not calculating that right now because I don't want to round it too early. You want to get all the other stuff done first and then at the end round it. So we'll add 3 to both sides, and then finally we'll divide by negative 2, so this whole thing gets divided by negative 2. Okay, the most challenging part of this problem might be actually entering that into the calculator, so let's make sure we do that correctly. So we will have the log of 14.4, and remember it's divided by, don't do 14.4 divided by 17 in the same log. Those are two separate logs in this problem right here. Log of one over log of the other. We need to put it exactly the same in here, otherwise it's not going to work. So we divide that, then we have to add 3, and then we divide by negative 2. And I suggest doing it in parts like that. To the 10,000th place would be negative 1.9707. That's the 4 decimal places. So negative 1.9707. Let's double check, and it is right. Easy way to check, by the way, would be take this number and just plug it in right there for m, and it should work. Okay, this next one is done the same way. Really the only difference is you could solve it the same way, but in this case it would probably be a good idea to take the natural log instead of the regular log, and that's because we're using e right here. Okay, so in this case we need to get rid of the 6 first of all. So we have negative 9 e to the 9m plus 3. 79 minus 6 is 73. Then we have to divide by negative 9. We always have to clear those numbers out first. That's to the 9m plus 3 equals 73 over 9. I'm not going to, negative 9, I'm not going to round that yet or calculate it because we want to get an exact answer. Okay, then what log should I take to get this to come down? I'll take the natural log. You could take another log, but there's a reason we're taking the natural log. Okay, e to the what power is e to the 9m plus 3? It's just 9m plus 3. That's why we took the natural log. And this is the natural log of negative 73 over 9. Last couple things we need to do here to solve for m, we need to take away this 3 right here, and we need to divide by this 9 right here. So whatever this number is your final answer for m, and that turns out to be the number that you see right there, negative 0.0838. Alright, these involve solving equations like we saw before. We have to put these back together though. So that's part of the challenge with these questions, is recognizing what we're doing. So in this case we're subtracting logs, and you might remember this property. If we are dividing logs and we expand it, that's the same as subtracting. So now if we want to go from here backwards, we have to divide those two logs. We're going to divide this number by this number, and we'll get 5. Now it's in log form, we want to change it to exponent form. So e, this number, to that power equals that answer. So e to the 5th equals x over 10. How do we solve for x? We multiply both sides by 10, and x equals whatever that number is right there, and it turns out to be 1484.1316. It's customary to round it to 4 decimal places, especially in a lot of science examples. You have to round it to quite a few decimals just to make sure it's not going to be inaccurate. Okay, same idea right here. We're subtracting these logs. That must mean we started out by dividing these two expressions. So divided by this, that equals 1. This is base e, so e to that power equals that answer. So e to the first is just e, and then we have this right here. We need to get solved for x, so I'm going to multiply both sides by 10. Okay, and then 10e is equal to negative 4x minus 4. We'll add 4 to both sides, so we get that right there. And then finally we get 10e plus 4 equals negative 4x. We'll divide both sides by negative 4 and put that in a calculator. That's going to be like negative 7, I think, or negative, somewhere around negative 7, negative 8. It turns out to be negative 7.7957. Alright, last couple examples. So these are on interest rates, compound interest, and one of them is compounded 3 times per year. The other is compounded continuously. So the regular interest formula is this right here. P stands for the initial amount invested, R is the rate, N is how many times compounded, and T is time. So it says she invests that much initially, so $25. A is the current amount, which we don't know yet. That's what we're trying to solve for. 1 plus the rate is 2%, so 0.02. N is how many times compounded per year, and it's 3. And then this n and this n are the same, so it's going to be 3 times 16. So we have to put this whole thing in a calculator here. So 2925. You don't have to simplify it, but I'll just do it anyway. That's going to be, actually there is no way, there's no easy way to simplify that. So we'll just keep it 0.023, because that's going to be a repeating fraction. And 3 times 16 is 48. So we put that in a calculator right there. And when you do, you come up, whoops, I was supposed to move that, not draw the line. When you put that in a calculator, you wind up with $4,023.82. Okay, this one is slightly different, same idea, but it is continuous compound interest, so we need to use a different formula, which is the PERT formula. Okay, we start out with this amount, so $5,065. E, and then his rate is 0.08. And we're going for 15 years, so 15 times that. Okay, in this case 0.08 times 15 is going to be 1.2, so 5,065 times e to the 1.2. We plug that into a calculator and we wind up with $16,816.39. That's pretty good. 15 years and you've more than tripled the money. That's how continuously compound interest works. Last problem, this is the logistical growth and decay problem. This is going to be growth, so that's why this is a positive KT instead of a negative KT. So write the equation. Okay, well our equation should have this number filled in for it. It should have the K filled in for it too. Y stands for the current amount of people, and A stands for the original amount of people. So originally we had 3.4 million, currently we have 3.7 million. So let's take this and just plug our numbers in. So 3.7 equals 3.4 times e to the k, and then we're going from 2000 to 2006. So that means our time for years would be 6 years. Okay, we need to solve for k, so we're dividing. First we divide by 3.4. Okay, and then how do we get that k to come down? Right now it's e to the 6k. We get the k to come down by taking the log, and it should probably be best to take the natural log because those will cancel. And whatever I do to one side I have to do to the other. So the ln of that, we're going to divide both sides by 6, and k is going to equal whatever this is right here. Notice that we're taking the natural log of that whole number, not two separate natural logs. So k equals whatever that is, and let's find out what that is right now, and then we'll write the equation. So the natural log of 3.7 divided by 3.4, and then we divide that by 6, and we'll store this value. That's the rate of growth. So STO alpha, we'll store that as k. So 1.4% growth per year. So 0.014, let's call it. Okay, so our equation, like we said, we need to have variables in it, so we need the y and the t. Our initial amount is 3.4, so that's this number. And then we found k to be 0.014. So there's our initial equation right there. Whoops, and that matches up with this. It says use this equation to predict Oregon's population 2020. Well, in 2020, that's going to be 20 years after 2000, so we just need to plug in the number 20 right here for t. So 0.014 times 20, we basically plug that in, and it's going to give us a number of 4.5 million. And then the last question says, using this equation, when will Oregon's population reach 6 million? So that means y, the current amount, needs to be 6 million. And we're still going to have this, and now the question is asking us when. So that means we're asked for time. We don't know what that is. So we're going to leave it as a variable. So we'll divide both sides by 3.4, and we will get this. We will get e to the 0.014t is equal to this number right here. How do we get the t to come down? We'll do it by taking the log, the natural log of both sides. These will cancel, and we'll get 0.014t is equal to this number right here. Last thing is divide by 0.014, and whatever that is the amount of time needed to get 6 million. Let's check that right now in the calculator. Oops, we have the natural log of 6 divided by 3.4, and then we need to divide that by 0.014, and that should give us 40.57 years. So when will be 40 years after 2040 and a half years, so sometime in 2041. Actually, you know what? Let me use the exact. That's inaccurate because we're using the rounded answer. So we stored 0.014. That's actually alpha k. So let's get a more exact answer. And it's still pretty close to 40.3, but it's a couple months difference there. So sometime in 2040, 2041, let's see if we got it, 2041. So that is Chapter 7 practice test.